right. I think it's clearly visible. So welcome again, everyone. Sorry that the first slot, the first talk didn't take place. So it's my pleasure to announce Frames here to give the first talk of this session about the core compiler and plundering around with it. And Frames is obviously well known in the Julia community for various contributions to the core language, also the differentiation interfaces, and yeah, take it away.
OK, hi everyone. So yeah, I'm Frames. I'm here today to talk to you about a way of doing IR transformations, really. So before I start, I just want to say this is a much better location for any conference. It only took me 26 hours to get here. This is like a huge improvement over Boston, which took me 48 hours to get to. Like 26 hours is basically next door to major common locations with many Julia users, like Perth, Australia. Very big city, not somewhere obscure like Boston. No one uses Julia in Boston. So more talks in this part of the world, please. What is this talk? So this talk is about writing custom optimization parsers in the same way that Julia itself does optimization parsers. This is in contrast to something like IRTools or even Cassette, which is re-implementing a lot of the analysis and modification utilities itself. We're going to reuse all the stuff that the compiler itself has built in to do it, and that has some advantages. So this is used extensively in DAE compiler, which is the kind of underlying mechanics for the CEDA system. It's used a bit in diffractor, not all diffractor, but some parts of diffractor use it. And it's also used in Will Tebbett's new AD called Taper. This talk actually came from like a small gist I wrote to show Will how to do some things which he wanted to do. So yeah, why would I want to do this? So one thing you might want to do is run a different optimization pipeline. The Julia optimizer is actually heavily parameterized with a bunch of different options you can configure, but you can't actually change most of them because you're not running the optimizer. Julia is. But you could, for example, enable union splitting with more than 4 elements. The other big case is you might want to say generate multiple functions from one definition. So DAE compiler generates about a dozen different types of Jacobians and callbacks and all these other things that SciML universe likes from a single function definition that it does a transform on. This kind of thing requires custom intrinsics, which I'll be talking about towards the end of the talk, and also some analyses, which you'll hear about in Kenno and Shuhei's talk tomorrow, probably. Yeah. So just a big warning before we start. This is very unstable internals. This is so far from what is safe and easy to use. It is relatively stable. It's not as unstable as you think it is, but it will break on minor Julia versions. But hopefully the core conception of what I'm teaching will be useful in an ongoing basis. Up on the slide is the version number that these slides have been tested with. But yeah, it works more or less the same on most versions. Another thing to note is a lot of the utilities are not in the base namespace. So people are probably aware, if you're at this talk, that Julia has 2 namespaces for a lot of things, core and base. A lot of the utilities live in Core.Compiler. Rather than in base, and that tends to break things like getIndex, which lowers the square brackets down to like a call to current module getIndex. So you need to bring those into the namespace of base, where you'll actually run your user-written pass. I've got an example for how you can do that up there. If you look into Fractal compiler IRTools.jl, that has for every version of Julia exactly which things you need to bring into the namespace, and it's probably the best way to work this out. So if you're at this talk, you're probably very familiar with this. If you're not familiar with this talk is not going to be very accessible to you. So we start out and we've got the source code. That's a string. Cool. So we parse it, and then we get the AST. So this is where normal macros run. This is normal metaprogramming time. We lower it and turn that tree into a list. We get the untyped IR. So this is when Zygote runs. It's where Cassette runs. Yeah. We run type inference, and then we get typed IR. So this is where the Julia optimizer runs, and this is also what we're talking about today, is running more things on this typed IR. Finally, we do code generation to get LLVM IR, which is where Enzyme runs, where GPU compiler runs. And eventually, you assemble the whole thing into machine code, and hey, you can execute that. Hopefully, that wasn't a surprise to anyone. So to kind of zoom in on what we're talking about, we're talking about this this typed IR. So I'm going to make the perhaps moderately bold claim that both the AST and the lowered IR are simple lexical transformations of the source code. There is no semantic information in here. It's not until you have types involved that you can really talk about the semantics of what the code actually means. I mean, we can't even resolve dispatch without knowing the types. So I'm going to say the typed IR is kind of the first level where we can really process the code in terms of what it actually means. So it's actually, I think, a really good place to run your code transformations, because you can do advanced analysis. So if you've used the @code typed macro, you've seen code IR. You've seen the code info object, which contains typed IR. For this talk, we actually want a relative of that. We want what's called the IRCode object. It's just a different internal representation of kind of the same information, but with a few extra things that's going to be useful to us, which I will show you in this talk. So if you look at this code up here, this is what we're talking about. We have some function quux. It does some things. It's got some branches. And if you look at the code IRCode, we can see, oh, look, it's a list. It's all in single static assignment. It's got some code. It's flat. It's got some jumps. It's fine. This is the kind of code we're talking about transforming. So to break down the parts of this talk, the parts of this code, the main thing we can think of it as is being a list of instructions. So an instruction has a number of parts. So the first part is the part we think about the most, the statement, SMT. So that statement is the expression. It's what it's going to do. Then we have a type, because the type is what we got for typed IR. But actually, when you look at this thing, the type isn't just the type. This is actually anything that's being stored in what's called a lattice, which I think you'll probably hear about a bit more from Kenno and Shuhei tomorrow. So there are other things that store in here, like information about, hey, this is actually like the constant 5. The other one we have to concern ourselves with is the flags, which I'll talk about a bit later. An important thing to note when working with these instructions is to always use this square bracket colon statement and those other square colon forms, not dot statement. The fields of these objects are very scary and nasty, and they don't work the way you think they would. But we have this get index overload, which makes it easy to work with them. So I said the main bit was the expression. So people should probably be pretty familiar with expressions, because you see them in ASTs all the time when you're working with macros. The only thing special about this in the IR is that it is in what's called single statement assignment. Basically, each statement only is single, and it's assigned to its position. So we can have its position is 1, it's the first position. And then we can have something we're assigning to it. But this one, foo brackets 2 times 2, close bracket, that's not a legal single statement assignment, because there's 2 statements there. There's the 2 times 2, and then there's the call foo on it. So it actually needs to be broken down into 2 statements. So first we're going to multiply 2 by 2, and then we're going to call foo on the result. Not too surprising, I think. So you've seen this before. We have SSA values. So those represent both positions and values, because a value is always assigned to hold its position, or a position is assigned to hold its value. And yeah, you can see here that you just see this %1 that shows up and %2 that shows up, where in the place of basically a variable. Cool. So arguments are the other thing, which is very closely related to a SSA value. They're basically SSA values that only have values. They don't have positions. They're just the arguments to the function. So you can see here the code for plus. It just calls addInt on the second argument and the third argument. The first argument is the plus object itself for the function. Yeah. Literals. So we're all familiar with literals like one and like a string like hello. But you can actually put any literal into the IR. You can do that in Julia itself just using like add eval and interpolate them in. And if you look at the IRCode, we can see that it's actually interpolated in the value there. This does have weird effects. Like you can mutate that thing, and it will persist the mutations across the calls because it actually lives in the IR object. It doesn't live in a variable. But yeah, you can see that there. We can contrast that to if we hadn't interpolated it in, which has this big pile of code where it's actually constructing at runtime rather than having it pre-computed and constructing at compile time. In general, it's really useful to insert literals because you can often work out, say, a tuple of indices that you needed to know, and you can just compute those all at compile time and insert them straight in, rather than having to like insert the code to generate a tuple. Invoke and call. So again, everyone should be pretty familiar with call. It's what calls a function. In IRCode, we have a second one called invoke. Invoke is like call, but we get this extra first argument before the function, which is the method instance. So invoke is used when there's a static dispatch where we know which method instance we're going to hit because we've run type inference and have predicted what methods we're going to use. So invoke, yeah, invoke's better because it's fast. It's what makes Julia fast. But generally, you don't want to write it because working out what methods you're going to hit is annoying. So generally, if you're inserting them manually, you can just insert the call, and then you can just run type inference, and type inference will convert all the calls into invoke if it's inferable, which is good. It's good to just reuse the stuff type inference does, at the cost that you are having to run type inference probably a second time, and maybe a third time, depending on how much stuff you're doing. OK, cool. So basic blocks. So let's see. Can you actually see all my code? You cannot. That's OK. There's nothing much missing at the bottom anyway. So we started out with code, which is like a Quux, and that's an expression tree. Like it's got all these branches. The if statement is a branch away from the other statements. But when we do lowering, we flatten it down into a list. The typed IR is just a list of instructions in order. However, we do need this structure. This structured information is actually very useful to us because we want to know things like what variables have been defined. We want to know possible paths you can take through the code. To do that, we have a structure called the basic blocks, where we break down paths that you can take through the code into sections that are always in front of each other. And you can see those here on the code where we've got this. There we go. We've got this one. This is the first block. It's got 2 statements in it. And then we've got 2, which is the second block, and it's got some more statements in it. Yeah. So then from the basic blocks, we can construct what's called a control flow graph, which is every possible path through the code. And you can see here, these are the possible paths through the code we have on the slide before, where you can start here in block 1, and depending on the result of the if, you'll either end up in this block, or you'll go straight to this block. And so you can use that to do various kind of analyses, and it needs to be maintained. It's one of the things that you get from IRCode that you don't get from code typed. Yeah, these things have previous and successor, like a general graph structure. OK. The other weird thing, so even if you're familiar with Cassette and Zygote and stuff, you won't have seen before, is these things called a phi node. So a phi node is basically, it's basically like an if-else, where the condition is what block I came from. So this phi node up on screen says to return the value %8, SSA value 8, if I was previously in block 2. Or if I was previously in block 4, return %17. It's basically, it's got hysteresis. It knows where it came from. It's kind of almost the opposite of a go-to. It's an if came from. And you'll see those anytime you work with code that has any kind of branches in it, basically. Yeah. So, on to how to do things with this structure. So a basic thing you might want to do is replace an instruction. So To do that, we're going to get out the instruction. We do that by indexing the IR object with the SSA value. Now we're going to change the statement to be some new statement here. We're just going to set the info field there to no call info because we're not doing anything special. And then if we know the type, then we can put the type here. But if we don't know the type, we can just put any here. And then we can add this flag, IR flagged refined. And that says that when you go and run type inference, please go and find the type for this thing. It's changed. You need to run it again. You don't have to. You could just leave it as any. You could not run type inference again. But the net result will be your code will be very slow because all your dispatches will be dynamic, which is generally not desired. But it does speed up your compile time, so maybe you want to do that. Deleting instructions. So functionally, we do not delete instructions when working with this structure, because if you delete an instruction, you make all of the IR numbering wrong, and it gives you no real gain. Instead of deleting the instructions, we just set the instruction statement to nothing and the type to nothing. And that will then have no effect on what actually runs. And when LLVM runs, it will delete this instruction anyway, because it has no observable effect. Inserting instructions is a bit more complicated. So we have this new instruction, which takes a statement of type, info, which defaults to none, line, which defaults to copying line above, and flag, which it works it out. But mostly you just pass in the statement as type, which, again, you could pass in the type as any and the flag as refined. So you get this instruction, and then you're going to insert it with insert node at the position. Attach after just says that if I said position 1, does it attach it at the 0th position or the 2nd position, depending on how you count it. Inserting instructions. I guess the other thing that's kind of interesting when inserting instructions is if you're trying to do something non-trivial, you might have to insert a lot of instructions. That's a pain. I recommend against doing that. Instead, you can just go and create a little function locally to do the thing you want to do, and then interpolate that function in, and then when you run the optimizer again, it will inline all that, and it'll be as if you'd manipulated the code to do something more complicated, and that's easier than directly creating like 10 instructions to do some non-trivial operation. So the other thing to note is that when you insert a node, it's actually left pending. It's not actually inserted. Immediately, you can see here it's up in green. And what's actually done is it's recorded this as a pending insertion at this location until we run this compact instruction. And the compact instruction, basically, it says go through and insert all the pending nodes to be inserted, because we don't want to insert them immediately, because if I insert like 5 of them, that would involve renumbering all the IR 5 times. So we just pen them all for later and run compact. The downside of this is a whole pile of other transforms you might want to do. Probably assume there are no pending nodes, so you may have to call compact every time you start a new optimization pass, depending on what you're trying to do. But yeah, basically go through, insert a bunch of instructions, do whatever you like. At the end, call compact, and you get back new IR that has all the new code that you've changed. Yeah. The other more advanced tool that I don't have time to really go into today is this Core.Compiler incremental compact. What this lets you do is lets you iterate through the code, compacting it, while also making changes. So you can express your whole problem as like a series of calls to incremental compact that just loops over the code again and again, each time fixing up the pending stuff from the last. But it's a bit harder to write, and it's a bit more fiddly. And yeah, this talk I only have half an hour, so I can't do it. But I recommend incremental compact if you're really getting into writing optimization passes. Cool. The last kind of special feature I want to talk about is what's called a custom intrinsic. So for our purposes, a custom intrinsic is something that has special handling by our custom pass, and that doesn't end up in the final code after our passes are all done. So a major use of this is to push things into a custom lattice during abstract interpretation, which you may hear about from Keno later on during the conference. But yeah, I'll show you kind of how it goes. So to insert a custom intrinsic, we basically want to create a function that has no real effect, but that definitely ends up in the code that we're going to observe. So to do this, we need to turn off inlining, so we know inline it. Otherwise, it could be inlined away, and we wouldn't be able to go and identify it during our pass. We need to put a compile barrier const here so that it doesn't ever get constant folded and thus deleted from that. And that's generally enough to make sure it won't be deleted. However, if you also need to avoid it being deleted due to dead code elimination, say it's on a pass that is provably not taken, but for some reason you want it to like show up anyway, which is an unusual thing, you can also add a base.do-not-delete inside it, and then it won't be able to be deleted even by dead code elimination. The other thing you do is you declare its effects using assume effects manually. You could also insert these effects later in post-processing, but generally we want to like just do this here, and then we can just update it with whatever we replace it with. So here I've added the no throw and the effect free, which is generally true for most things I've seen custom intrinsics used for. To show you a bit of, show you how you kind of use this. So we can go through all the IR statements. We get out the instruction, we get out the statement, we check, is the statement an invoke? Yes. If it's an invoke, is the type, that's the argx type, args2, if you call singleton on that, which just converts types into singleton instances of those types, is that compile datetime? If so, we're going to replace the instruction with datetime.now, and which has type datetime. So this custom intrinsic basically inserted into our code at compile time the current datetime that it was being compiled at. I don't know what this is used for. Someone might want to use it. It's a kind of novel thing that you can do with a custom pass that I don't think you can do very easily in other ways. But yeah, that's a custom intrinsic. So to talk about how to kind of hook this all together and run the full compile pass pipeline manually, the first thing to do, you want to get or create from scratch this IRCode object. So you can either get one and then transform it, or you can create entirely based off from scratch. You're going to run inference on it. You're going to run optimization on it. And you're going to give it to an opaque closure and tell it to compile that into executable code. That's not necessarily the intended use of an opaque closure, but it is a thing you can do with an opaque closure right now. Valentin next might talk about kind of the more future sensible way to do this, or he might not. Valentin is shrugging. So I'm going to go through these kind of steps. So how do I run? I've already talked about how to kind of transform and create these. So how do I run inference? So here's the code that you actually use to run inference. So we get an empty method info object. We look up the world age. We get the spec type. So this is the types we're going to specialize on. Here we're just reading it from the IR.arg types, the IR that we're passing in. And we get the interpretation state, which is made up of all these things. And then we run this Core.Compiler IR abstract constant propagation. Effectively, this runs type inference and constant propagation. That's how we run it. So to do this, we're going to need some parts. We need the IR code that we've already generated. We need an interpreter, and we need a method instance. Basically, where we're going to put it. So where do I get an interpreter? If you have a custom interpreter, then you already have a custom interpreter. Yay. Assuming you don't, you probably want to use the native interpreter. That's the one that is built into Julia itself. So this thing is Core.Compiler native interpreter. It has two sets of parameters. It has the inference parameters and the optimization parameters. So the inference parameters are stuff like this. This says stuff like maximum union splitting, how much to splat tuples, other things to determine kind of how hard it's going to try to infer things. It actually has a really good docstring. Bits of this has really good docstrings, bits of this doesn't. The other thing we've got is the optimization parameters. So this controls, in a big way, it largely controls inlining. So you can make it more or less willing to inline things. Do a few other things. Assume fatal throw says any exceptions can be treated as just fatal and won't occur, or if it does, you'll add error versus like actually needing throws to be able to be caught. There's a bunch of parameters here that you can set, and setting these is kind of one of the neat ways you can reconfigure things. But yeah, we can create native interpreters. That's fairly straightforward. The other thing we need is a brand new method instance. So there's not much to this. We have this C call of this particular function you call that just gives you a new method instance. Then the only other parts we need is to set the specialization types and the module. So the only interesting thing here is we can take the argtext and we're calling this widen const on it. And that name is slightly deceptive. What it actually means is to discard all lattice information that isn't type. So the main source of lattice information that isn't type is the fact that something is a constant. Thus the name widen const. It just gets rid of the const part of it and leaves you just the type. But yeah, that's a case controlling what it should be specialized on when it compiles. And then to just bring this all together, we get ourselves a method instance, we get ourselves an inferred version of the IR on that second line. We create the stuff to run the inlining pass, and we compact. Then we run the SROA pass. What's that? That's scalar. There we go, scalar replacement of aggregates. It basically turns structures where you access the fields. It basically deletes the structure and just leaves you with the fields, which gets rid of a bunch of get index operations and things like that. We do the ADCE pass, which is the aggressive dead code elimination, and again, we compact. And those are kind of the actual main optimization passes that exist in Julia. So by running that set of things, you've basically run the optimizer at this point. And then we verify the IR to make sure we haven't made anything illegal, and pass it to the opaque closure. So you can insert kind of your custom passes either before or after inference would be the normal place to run them. Or you might want to insert them like after you do some of these things and maybe do them again later. But that's basically how you use this. Cool. Yeah, just some final points. So if your code segfaults, it is really, really easy to make things a segfault when you work at this level. The first thing to do is to use verify IR, and that checks most of the assumptions that the compiler makes. I would say that if you've got code that segfaults, it's worth opening an issue and being like, hey, is verify IR like not capturing this? Or am I doing something sufficiently obscure that verify IR can't catch it? In particular, if you are using incremental compactor that I looked at earlier, you need to make sure you're not modifying the IR that is being compacted while you're compacting it without using the incremental compactor interface. Yeah. But if all else fails, run Julia in GDB. It's awful. But it's also like kind of the only thing you can do to debug a segfault. I would really appreciate if someone would run like a whole JuliaCon talk just on using GDB, but yeah. To conclude, let's talk about what you can do now. So you should be able to now understand the optimization part of the compilation pipeline really well. Hopefully you'll be able to write IR transformations to use the compiler's own utilities to do your own cool custom transformations. As a fun challenge, you can write a function decorator macro that does the IR transformation of your choice on the function it decorates. If someone does this, or wants help doing this, come bother me during, I don't know, the hackathon or during a break. I've done just enough code to prove you can write this as a decorator macro. It's neat. You can make a function that does more optimization than normal. Yeah. Cool. That's all I had. So,
thanks so much.